Okay, so here we're looking at sampling strategies. And these are just some different techniques that you can use in order to effectively either gather your own sample or to critically look at someone else's secondary source of sampling. It is always a source of bias, and that'll be our next topic. So sampling bias is usually one of the big problems that we have. If you don't effectively use a sampling strategy, then you won't have a good sample. So let's talk about what a good sample is, and then we'll talk about some sampling strategies that you can use. And you can read most of this in your textbook. So these are just little bits and pieces that I've added along the way, but this is, sort of a companion to your textbook in section 2.3 of the old textbook. Okay, anyway, so sampling strategies. First of all, let's talk about really what we're talking about, which is a population. That's the group of individuals that we want to talk about. We want to summarize, we want to make predictions about, we want to do statistics on. Okay, so it's a group of individuals one intends to study. This value must be carefully defined. You have to know what your population is. You can't just sort of go out there and say, oh, whatever, because you want your sample to reflect the characteristics of your population so that you can have an accurate representation. Otherwise, if you just go out and just take any people from your population, you don't even know what your population is, then you don't know what your data summarizes. Okay, so usually this is a starting point, and most people know pretty well what their population is. But again, you need to define it. Because your sample can be accurate and inaccurate based on what it's defined as. For example, you could take an entire classroom, and if the population is the classroom, and then you take a small group of individuals from that classroom, then you would want to have it, reflect the demographics of that population, and so on and so forth. Equal number of male, or proper number of males and females, and people of different backgrounds and ages and all sorts of things. Also, if you define your population as the entire school and you take a grade 12 data management class, it's a small, very sort of specific set of individuals. If your population is grade 12s, it's a little bit more accurate of a sample if you take a classroom. But if it's the entire school, then it's a less accurate sample. If it's the entire, city of Mississauga, then it's way off. Okay, because you know that you're really getting only a small subset of the people in the population, a small group of the people in the population. So it's important for you to know who you want to define as your population, who you want to summarize, so that you can understand and sample accordingly. Okay, and of course, next step is a sample. So I have different ideas for examples. So you can use the notes that I have. I've used some examples in your notes as well. Or you can look at the examples that are in the textbook. Or even from what I'm dictating to you right now. Okay, so a sample. This is a collection of some fraction of the population. Very often we use subset as a word to go along with the fraction of the population that you intend to study. Again, this is a smaller part of the whole. Okay, a smaller grouping. Okay, and it is an approximation of the population as a whole. Now, how good of an approximation it is depends on whether you meet these criteria. First of all, the largest sample that you can get is actually the entire population, and we call that a census. Okay, and that's where your sample size is a capital letter N, so you can see that, capital letter N. Okay, and the closer you get to, of course, the full population, the more accurate your statistics are going to be, because you're going to have just about everybody measured. Okay, so you're going to have basic truth out there. But if you do take a sample, a smaller and smaller sample does tend to move further and further away from being the most accurate summarization of the population, but it doesn't mean it can't be a good summarization. Okay, it depends again on how you derive it. So again, there's all kinds of problems with sampling because obviously you'd want to take an entire census all the time, but that's very difficult to do. Sometimes either A, it's very expensive and time consuming, inconvenient, time consuming, but also sometimes you find yourself in a situation where having a census is just impossible. If you want to take a census of all the fish in a lake, you have to catch all the fish. That's impossible to do. Okay, so if you're measuring something that's very difficult for you to gather everybody together in at once, a census is impossible. So you want to, of course, use a sample, and sometimes you have to use a sample. But sampling is expensive. Okay, it takes a lot of time and money and effort. It's inconvenient, okay, because it takes some time and you have to think about things and plan things out. It can be very time consuming. I had some friends who were sampling over a 10-year period for their PhD thesis. Okay, to do a study. By the time they got to the end, some of their data was so old because the population had changed that they couldn't really use it. But again, they had to develop this window. So this can be a very time-consuming process. And it can be inaccurate, even if you try your best to be as accurate as possible and to plan things out. So the first thing you need to do is you need to plan your sampling technique, and then you have to hope that other characteristics fall in line. So how do we sample effectively? Okay, well, any sample has three characteristics that make it effective. First of all, it's random. And random just isn't the word, oh, any random individual. Random means the chance of any individual member of the population being sampled and measured is equal for all members of the population. That's difficult to do. Okay, even when I answer questions in a classroom, I generally tend to ask questions of the students who are furthest in the front. So we get sort of a disproportionate amount of individuals who are sampled from a front. Does everybody have an equal chance of being selected? No. People put up their hands. I'll choose people who put up their hands. Why? Because I feel like people who don't put up their hands either A, don't know, or B, are a little bit, shy about including their information. But their information is still relevant. They're still a member of the population. Okay? So again, you want to make sure that everybody has an equal chance of being selected. That's random. It's not too difficult to be random, but you have to use some tools in order to do it effectively. You also want to make sure your sample is representative, and that's a pretty big deal, a pretty big idea. What it means is, and this is the definition, the collection of the individuals sampled, your sample, is a true snapshot of the demographics of that population. And what demographics mean is it could be your age structure. So if there's 10% of our class who are grade 11s, so 16 or 17, and then most of our class is grade 12s who are 17 or 18, and then we have some senior students, especially in night school or summer school, we could have people, I've had people in class who are in their 60s, okay? So we want to make sure that our sample would represent all of those individuals in a proportional manner. If you're going to sample 10 people from a class of 30, and most of them are grade 12s, and you should sample the grade 12s mostly, but you should still have maybe one individual who's a grade 11, and then maybe one individual, if they're not a large enough amount of people who are older than grade 12 in the classroom, and then sample someone from that grouping. So that's what I mean by the demographics. And demographics could be male-female ratios. Your sample has to have the same ratio, male-female, as your population. It could be, like I said, age structure, grade structure, school ability level structure, if anything that's relevant. It could be, if you're asking something about socioeconomic status, and you have to have people from all sort of walks of life and all backgrounds economically and socially. If you're asking questions about religion and it's relevant, or culture, then you have to have people from all cultures who are proportional in that population. So if our school population has a huge amount of people who are Muslim, I want to make sure that I have a proportional amount of Muslim people, and maybe there's only a few people who are Hindi. Okay, then of course I wouldn't have as many people who are of the Hindu faith. Okay, and so on and so forth, or from different backgrounds as far as countries or whatever it may be. So whatever statistic is relevant, that's what I'm talking about, demographics. You want to make sure that they're represented in a proportional manner. So representation is pretty important for a good, accurate sample. The last thing you want to do is you want to make sure that it's unbiased. Now we're gonna talk more about sources of bias. Okay, but that means that one individual doesn't have there's no favoritism of them being selected, of them being measured, or of measurements being preferred, or of results being preferred, or even interpretations there and afterwards being preferred. And there's a whole lesson that we do on bias and bias, sample bias being one of them. Okay, so again, we want to use some of these techniques to eliminate sample bias. So a good sample has these three characteristics, and they're important ones to keep in mind. Okay, so what techniques can we use in order to make our sample more random, more representative, and more unbiased? Well, we'll talk a bit more about bias later on, but we're going to focus on random and representativeness. Okay, so the best way for us to be random is to do a simple random sample. Obviously, it's really good at being random. Okay, and what does that mean? Well, it means that we use some sort of tool in order to assess who it is we're going to select and who it is we're not going to select. Okay, so you could maybe assign everybody a student number, like we have in our classroom. Okay, and you guys know this classically, it's drawing names from a hat. But even when you draw names from a hat, you have to make sure that it's shaken all up. You have to make sure that everybody folds their pieces of paper in the same way, okay, before they put them in the hat, and so on and so forth. So to make it a true random sample, you want to have uniformity so that everybody is treated the same. One way that you can do that, with a computer or with a graphing calculator, or even a lot of calculators, or an app on your phone, is to use a random number generator. But you have to have a label for individuals, whether it's their name, drawing from a hat, whether it's a student number, whether it's, how they choose jury selections, where they use the roll numbers for people who are taxpayers from that particular municipality or wherever it is that they're sampling from, whatever it is they use. Maybe it's social insurance number. I can't remember what they use for jury duty selection, but it's a random process, okay, where everybody has an equal chance of being selected. Okay, so if you use one of these random number generators, then it's a great way to make sure that everybody's an equal chance of being selected. Okay, and so there should be no problems with randomness in that case. All right, so rather than, when I choose assignments for my grade 9 science class, for example, and they want to choose what element they want to do for their element assignment. I don't know if you ever did that for your class, but when they get to do it, they don't just get to choose and come up in first come, first served basis. The way it works is I have a random number generator in www.random.org, and I go there and it generates a sequence from 1 to 25, and I use the numbers on our attendance list. And so there'd be 25 students in class, so the first person in alpha is a 1, but every number is an equal chance of being selected. So that's a simple random sample. Now there's a systematic sample. A systematic sample kind of tries to make sure that people are a little bit more randomly selected, but also representatively selected. What you do is this, okay? Firstly, what you want to do is you want to rank all the students in some way, shape, or form. If it's alphabetical, you can do it alphabetical. If it's by height, you can do it by height. If it's by age, you can do it by age. And you rank them from youngest to oldest or oldest to youngest. Most people just go from youngest to oldest. And then what you do from there is you pick a sampling frame from there. And it's based on the number of individuals that you want. Okay, so if you take your population size, let's say there's 30 students in a classroom, and I line them up by height to find out something about the heights of individuals in that classroom. And then I have a desired sample size. So let's say I wanted to take, 15 kids out of 30. So I take the 30 out of the 15, and that means that I sample every tooth person. Now we don't call it tooth, we call it second. But every second individual gets sampled from that lineup of tallest to shortest, or shortest to tallest. So what you do is you start somewhere, and you can even randomly choose where you start. We'll talk about a hybridized sample. But anyway, wherever you start, even if you start with the first person, and then you go first, skip one, and then next, skip one, and then next. And you sample every second individual, and you measure their height, and then you write down all their heights, and you'll have 15 heights by the time you get to the end of the sample. If you start arbitrarily somewhere in the middle, and then you get a bunch of... So what you're going to end up with is a proportional number of people who are short, a proportional number of people who are like middle height, and a proportional number of people who are tall. Okay, and so you get a little bit of everybody. A great example for that is if people are lining up for a movie and there's a lineup, so they're pretty big fans. The people who are right at the front were people there who were waiting from the beginning, so they're super fans. The people at the end may have just shown up and said, let's go see a movie tonight. But what you're going to get is from super fan, sort of super fan, they just want to go to a movie to finally, I just showed up. Okay, and you get all kinds of different people from all kinds of different rankings all the way along the way. Okay, and it's a good way to be representative, because how you line up the people is the demographic that you want to make sure you get everything across all of it. Okay, or sample everybody from across all of the heights, or all of the ages, or all of the alphabetized sort of letters of the alphabet, that sort of thing. Okay, and so that's pretty good at being somewhat random, but really also being representative, okay, at least according to how you line them up in that demographic. The next example that I want to use is called a stratified sample. And a stratified sample means that you break things into layers called strata. Again, those layers are the relative demographic that you feel is most important. So if age is most important, you break up classes by age structure. 14, 15, 16, 17. Okay, if, height is most important to you, then you break them up by height categories. Short, medium, short, normal, short, average, and tall. I don't know what it is you're going to do. Okay, so what I'm going to use is the age structure for a school, and I'm going to break them up. And the strata I'm going to create that are relevant are going to be, let's say, I want to sample students on school issues. And what I want to do is I want to make sure I sample the right amount of grade 9s, grade 10s, and grade 11s. So let's say we break them up into grades. So that's the criteria that we stratify them with. So we go 9s, 10s, 11s, and 12s. And to do a proper stratified sample, you don't just want to take equal numbers of each. So if I'm not stratified, and I wanted to sample 100 kids because I have 100 surveys, then I take 25, 25, 25, 25. But if the population of the school is not proportional, and usually you tend to have more grade 9s and grade 10s than you would have grade 11s, than you would have grade 12s. Not always these numbers, I'm just making these up. Okay? But the idea is that if this is the way the population works out, then it means that the grade 9s and the grade 10s are getting underrepresented because they're the biggest populations. And the grade 12s here are really getting overrepresented. Okay, because there's only 150 of them, so 1/6 of them gets chosen here, and this is 1/12 here. So it's a big difference in the amount of say that they have. So if you want to make it stratified, what you want to do is you want to take a percentage of each group, or a proportion of each group that's the same as the proportion as the whole. So that would mean I would want to probably take an equal number of 9s and 10s, and then less 11s, and then even the smallest amount of the 12s. So what I would do is very often take a percentage therein. So this whole population is 300, 300, 600. That adds up to 1,000. So let's say I wanted 10% of the population, or 100 surveys. Okay, I would multiply that by 0.1. And so that would mean I would take 39s, 30 grade 10s, times by 0.1, times by 0.1, times by 0.1. So again, 10% of each. And I want to have 25 11s, and I only want to have 15 12s. Okay, and what you'll see is that my sampling is not 25, 25, 25, 25, but 30, 30, 25, 15. I'm taking the least amount of the smallest population and the most amount of the most population. And as a result, it's proportional to what's important. In this case, the strata is the grade. Maybe if I have a male-female ratio, now, usually male-female ratios in schools tend to be 50-50. But if I have a male-female ratio, then I would want to substratify that into male and female, male and female, male and female, male and female. And if that's the case, then I'm assuming that I would do 15 and 15 of males and females, and 15 and 15, and I don't know, I'd have to go 12 and 13. Or 13 and 12, right? And here I'd have to go 8 and 7, or 7 and 8. And here I took less males, so I probably want to take more males here, but whatever, I don't know. You do your best, because you obviously can't sample half of a person. And that would be stratifying your samples. So you'd break them into a relative demographic. And this is really good at being representative. Especially if you take things and subdivide them by the most important criteria, grade or age, and then you take things and you subdivide them by also gender, which is really important, because a male perspective and the female perspective may be very different from each other. And if those are relevant demographics, make sure that you hit on those in the right proportions, so that it's a proportional representation in the population, so that they can speak to their particular needs, or that the numbers can speak to their proportions in the population. So stratified and systematic are really good at being representative. Random is really good at being random. What is the best sampling technique? Well, I think the best sampling technique that you can have, okay, is a sampling technique where you actually hybridize all of them. It means you put them all together. Okay? And when you put them all together, those sampling techniques can be very, very powerful. Okay? So, let me give you an example of a sampling technique that we did. But this is, this should say is. It says id. So these techniques are effective in sampling, however, are most effective when used in combination in some way, creating a hybrid method that ensures a sample is random, representative, and unbiased. Okay, so randomness means you would use a random number generator. Representative would mean that maybe you use a systematic or a stratified approach. And then if you can combine all of those, then that would be the most powerful technique that you can do. And there's going to be a question in your sample where you want to take a sampling technique and combine all three of those. So this is an example, a line transect method. First thing that I did this when I was really young, really much younger, when I was in university, so older than you, but younger for me. I did this ecology study where we went into a marsh. And what we did was we standed on a road. This is basically the road right here. And then what we did was we took a protractor and we randomly sampled numbers between 1 and 18 using a random number generator. When we did that, we really were sampling degree measurements from the road. So we put the protractor along the edge of the road, and then we randomly sampled between 1 and 18. I can't remember what I got, but let's say I got a 5. That would mean I would go to 50 degrees on that protractor. So imagine a protractor sitting on the ground. I measure 50 degrees and I'd take off in a line. So let's say this was me over here, so I can actually do this. And I'd run a line, and this line would be a rope. And so we just have someone walk in a nice straight line. And this rope was like 500 feet long. So we just had one dude walk. It's straight, and had the rope as straight as possible. We walked through a marsh, so we were going by trees and tree stumps and all kinds of craziness through deep parts and shallow parts, but not that deep. So the person wasn't at risk of drowning. But anyway, we randomly sampled that degree value. Now other people got different numbers, so they would go off in all kinds of other directions, right? If you got 180, you went straight along the road and sampled along the road. If you got 0, same thing, sampled along the road. And if you got 10 degrees, you go off that way. And if you got 90 degrees, you go straight out into the marsh. And if you got, 117, then you would go off in that direction. So that's an example of a random technique to choose which direction you're going to into the marsh. So there's a random element to it now, okay, as far as which direction we went into. Then what we did is we used a random number generator to choose our stratification. And we choose a number between 1 and 5, and these were measured in meters. So this rope, we had a tape measure that went along this rope, but we tied the rope to a tree or something nearby, and then the guy walked back. And so what we would do was sample along this line. And what we would do is every 3 samplings that we would do, we would draw a number between 1 and, I think it was 6 or 1 and 10, I can't remember what it was. And we would get that number, and that's how many meters we would count. So let's say we got the number 4. So we would count 4 meters, boop, 4 meters, boop, 4 meters, boop, and sample systematically. So now it's a random and a systematic sample. Okay, because I'm combining a random technique to choose the numbers and a systematic sample because I'm sampling every so often. And then what we would do here is we would choose a quadrant in order to sample, and we would measure all the plant life and animal life in all these different areas around here. Same thing here, same thing here. Now we would take a number between 1 and 4, A, B, C, D, randomly choosing, and that would be the quadrant that we would sample. So let's say we got an A, we would sample this quadrant, or B, this quadrant, or C, or D. And then we would move on to the next one, and then sample there, and the next one, and then sample there, and the next one, and then sample there. Once we got 2 or 3 of them, we had to then generate a new random number. And when we generated the new random number, let's say it was 10, then we would go 10 meters, and 10 meters, and then 10 meters. Now you may say to yourself, well, that's not very stratified, right? Where's the stratification in there? When we got back to the lab and we had all our data, we had A's and B's and C's and D's that we sampled, and we looked at the number of A's that we had, and we looked at the number of B's that we had, and we looked at the number of C's that we had, and we looked at the number of D's that we had, and we grabbed samples. Now we did this for like 500 meters, so we did a ton, and we even worked our way backwards towards our original starting point. So this was an example of a hybridized sample that was stratified when we got back to the lab, because the data we chose to actually log and analyze afterwards was the strata. Okay, and we had to make sure we had a proportional number of A's and B's and C's and D's because we couldn't do all of them. It was just too much to analyze. And then how we actually chose our quadrats, this is the line Transect, how we chose our quadrats was systematic as well as, of course, random. So this was an example of a random systematic stratified sample. And so we used all those techniques in concert together, okay, to choose what it was we were going to choose and to create an accurate representation of that population of the marsh and all the animals and plants that were found in the marsh. Okay, there's other sampling techniques that are used that have some characteristics to them that are great. Okay, so rather than write these all down because it'll take me too long, I'll give you some examples orally of how these work. A cluster sample. So the cluster sample, it isn't perfectly hybridized. It isn't perfectly random or representative, okay, but it's a sampling technique that's used very commonly, and it has its pluses and minuses to it. Okay, so a cluster sample is a small collection that is localized geographically by some other means in the hopes that the cluster is still represented